Now, continuing from the previous video, we're going to take a look at the next step. Says let's solve the same problem using determinants. So we go back to our equations. 25 volts equals 680 by 1200. Each of those related to the currents through those resistors R1 and R2. 25 volts equals to 1150 I1 minus 470 I1 and I2. So you'll have to go back again to verify the setup here for the current I2 by making sure that we have the correct values set up here. We're going to have each of these elements that we're going to pull from these two expressions. Okay, so just refresh yourself. So if we take a look at it, we have A1 and A2 here in the first column, 25 and 25 in the second column. Here we have A1 and A1 in the first column. Here we have B1 and B2 from the second column. So we've got this set up with each of the elements for current I2 ready for the determinant. So you recall this times this minus this times this times this minus this times this. So we've got that shown in the expansion here for our next step, and are able to solve using the determinant method I2 as 6.91 milliamps. So if we take a look at the array, just as we chose from the expansion up here, each of these terms, A1, B1, K1, A2, B2, K2, are the elements of each of those expressions. So if we put them in determinant form, you can see A1, A1, A2, B1, B2 in the denominator, K1, K2 in the numerator, B1, B2 in the numerator. We do our expansion, this times this minus this times this times this minus this times this. We end up with the expansion and are able to solve for current I1 then just by doing the math, 24.6 milliamps. So these values for the two currents I1 and I2 agree with the values that we found in the substitution method. So, I hope that you're gaining an appreciation here that you can solve these simple circuit these analyses by several different methods. The calculations to find the current I3 through R3 and the voltage drops are the same when using the substitution method. Differences between the voltage drops or currents using the various methods are due to any rounding error, and you should be becoming familiar with that. As you enter values into your calculator, you end up with different values that may vary for rounding area. So in the next set here, 14.7, we're looking at creating circuits that have more than one source. So if we find the currents and voltage drops in the circuits for 14.6 below using simultaneous equations, we first have to determine the direction of current in the different branches. So we have to look at the polarities involved so that we make sure we have our positive and negative signs showing the direction of current across each of our components. We've got three resistors here, again, R1, R2, and R3 in a little different configuration here, and the configuration will depend on which side of the schematic that the resistors show. So we first have to determine the direction of current in the different branches. If the direction of current is not obvious, we simply assume a direction. So if we assume a direction, you make sure that the other direction then is just the opposite. How would we do that? Well, if you look at these sources, you've got the long bar, short bar, long bar, short bar. On this side, you've got the short bar, long bar, short bar, long bar. And from those, you could say, okay, I'm going to assign a positive at the top of the long bar and a negative at the top of the short bar. Once you do that, once you establish your convention, you have to stick with it throughout your analysis. So let's assume that the direction of current results from source E2 on the right side. The resulting polarities then would be shown in the other schematic representation, 14.7. There are 3 loops. One loop includes the voltage source E1, R1, E2, and R3. So pretty much what we've done is we've gone through the outer circle, the outer boundaries of the schematic. A second loop includes E1, R1, and R2. So that is our first inner loop in the schematic. The third loop includes E2, R2, and R3. So that's our loop on the other side here. So we're going to determine our current flow and stick with it throughout our analysis. Even though there are 3 loops, we need only use 2. Let's use the loops then that contain E2. Okay, so we're only going to look at the loops that contain the source on the right side. So the source on the right side, E2, minus the voltage drop across R2, minus the voltage drop across R3, and set that equal to 0. So we've created this loop on the far right side. Rewriting the expression then, E2 is equal to V2 plus V3. E2 minus V1 plus E1 minus V3 equals 0. Okay, so now we're including both of the voltage sources and the voltage drop across R1 and the voltage drop across R3. So this is our outer loop analysis. So we have E2 plus E1 because the sources add, in this case, because the polarities are set that they add, plus, minus, and our voltage drops across R1 and R3 then add. So we've created 2 loops for us to start doing an analysis. E2 and E1 are both included in the left member of the equation only because they are both known. Substituting the known values, we get E2 is equal to voltage drop V2, V3, and go back and look. You can see we have 40 volts given and 20 volts given for E2 and E1. So we substitute 40 volts is equal to V2, V3. And then if we look at the summation of those 2 sources, 40 plus 20 gives us 60 volts is equal to V1 and V3. So that's our outer loop. Expressing the equations 1429 and 1430 in terms of the current resistor drops, IR, we get 40 volts is equal to V2, V3. Now we're going to make a substitution. V2 is equal to I2, R2. V3 is equal to I3, R3. And we can then substitute our values for each of those resistors, 3K ohms, 1K ohm, times the respective resistance. In the next one, the outer loop, we have 60 volts is equal to the voltage drop across R1 and R3, V1, V3. Make our substitutions, our substitutions, and we have 2K ohms times the current I1 plus 1K ohm times the current I3. So let's take a look at the equations then, 1431 and 1432 together. So we end up with 40 volts is equal to 3000 I2, we just took the K out, plus 1000 I3. 60 volts is equal to 2000 I1 plus 1000 I3. So in this case, we still have 1, 2, 3 different unknowns in here that our currents are given. So if we assume that the current through R3 is the total current, I3 is equal to the sum of I1 plus I2, which makes I1 equal to the difference then of I3 minus I2, substituting E3, I2 for current I1 in the equation 1432, we can eliminate one of the unknown yields. Okay, so we're going to try to simplify things by getting rid of one of those currents, eliminating an unknown. So I1 is equal to I3 minus I2. We make that substitution. Now we have just I2 and I3 in our expression. We gather our terms. 2,000, 1,000 gives us 3,000 I3 and 2,000 I2. Now let's put the equations 1431 and 1433 together. So there's 31, there's 33. We're going to put them together and solve. So we have 40 volts is equal to 3,000 I2 plus 1,000 I3. That's this expression up here. And 60 volts is equal to minus 2,000 plus 3,000 I3. So that's this expression here. So now we've got two sets of relationships with two unknowns. Okay, so there are our values. Again, there are our expressions. So let's do a solution by addition and subtraction. So if we multiply the top expression, the first one, the 40 volt expression, by 3, we can cause the coefficient of I3 in both equations to be equal. So 40 times 3, 3,000 times 3, 1,000 times 3 gives us 120 volts, 9,000 I2, 3,000 I3. Now we can put the equations 33 and 34 together, and since we're looking for a difference, we can solve by subtraction. So we're going to subtract the two expressions from each other. In doing so, we cancel out or eliminate the I3 expression, 3,000 minus 3,000, and by subtracting, we add 2,000 to 9,000, which gives us 11,000, and we subtract 60 from 120, we get 60 volts. So now we have a very simple expression, 60 by 11,000, which gives us 5.45 milliamps, or current I2. So now if we substitute current I2 back into the second expression, 120 volts equals 9,000 plus 3,000 I2 and I3, we make that substitution. Now we've set up the expression to solve for I3. So we get 70.9 volts is equal to 3,000 I3. Divide 3,000 into 70.9. I3 then yields a value of 23.6 milliamps. So if I3 is 23.6 milliamps and I2 is 5.45 milliamps, we go back to the expression that we solved for current I1 as the difference in I3 and I2, and we get I1 equal to 18.2 milliamps. So with that in hand, we have our three currents. We already knew the resistances. We can plug those values back into the expressions IR1, IR2, IR3, and solve for V1, V2, and 3 voltage drops. And we end up with 36.4, 16.4, and 23.6 volts. So those are all of our currents. We know all of our sources, and now we know all of our voltage drops. To verify then, we can apply Kirchhoff's voltage laws to the loops. Okay, so in this next one, we are going to do a solution by substitution, and hopefully we come up with the same answer, and we will do that as our next iteration.